Would anyone believe that there would be a revolutionary use of technology on genes that could have an effect on the genes of every individual in a growing population forever? Hello and welcome to another episode of My Little Protein. I am your host, Farida Marzouk, and today I will address an issue found through a harmful disease, Huntington's disease, or HD. According to PSOS, HD affects 1 in every 10,000 individuals, with around 40,000 people being affected by the disease in only the US. Thus, this disease has caused harm to many individuals around the world, and the cure is in progress by the use of modern technology, genetic engineering known as CRISPR. To start off, according to Mayo Clinic, HD is a rare but very severe inherited disease that causes nerve cells in the brain to break down progressively, which results in physical and mental issues that appear over time. According to Huntington's Disease Society of America, over the course of 10 to 20 years, someone with Huntington's disease will lose their ability to work and manage tasks, and eventually not be able to walk, talk, eat, and drink, in which the patient requires professional care and people to support. On top of the physical effect, patients can get depression, OCD, personality changes, forgetfulness, impaired judgment, and so much more. Based on NHS, the National Health Institute, this disease usually occurs to people between 30 to 50 years old. According to Brandon, having Huntington's is as bad as having ALS, Parkinson's, and Alzheimer's simultaneously. It is said that there is no cure for this severe hereditary disease. But what if there is? So how is the process used specifically for Huntington's disease? Well, according to PSOS, HD is an autosomal dominant disease, so that means that having just one copy of the mutated gene would be enough for this disease to be expressed. According to Johns Hopkins Medicine, the gene for this disease is a single gene called Huntington, HTT, found on chromosome number 4. Having CAG, cytosine, adenine, and guanine repeats of 40 or higher in the HTT gene is what causes the disease. And if the HTT gene is mutated, the individual has a high risk of developing Huntington's disease through a dysfunctional protein. Unlike normal Huntington protein, when an abnormal Huntington protein is produced, it will clump in neuron cells and thus cause the disease. According to Professor Dave, clustered regularly interspaced short palindromic repeats, also known as CRISPR, are short and repeated sequences of DNA that can be read in the same way from 5' to 3' on one strand of DNA and as 3' to 5' on the other strand. Based on Science Direct, in the case of the HTT gene on chromosome 4, these repeats that can be read in both ways on anti-parallel strands of DNA have excessive amounts of these CAG repeats, which cause the mutation resulting in HD. Also stated by Professor Dave's informational video is that CRISPR was originally used as a defense against viruses, specifically bacteriophages that attacked the bacteria, in which bacteria had to resort to their stored CRISPR region. Once a bacteriophage invaded, its DNA is placed in between repeats, palindromic repeats, of the CRISPR region, known as spacers. When this happens, the virus is no longer foreign to the bacteria. Then CRISPR is transcribed from CRISPR RNA, known as crRNA. The protein Cas9, which actually cuts the mutations, attaches to the crRNA along with tracer RNA, which is complementary to the palindromic repeats. All three of these entities are attached together to make an effector complex that can invade a virus once it enters the bacteria again. The effector complex recognizes the viral DNA and it will attach to the crRNA, which is designed to be complementary to the virus, and Cas9 will snip both strands of the DNA to neutralize the virus. This process was then found that it could be manipulated in labs by researchers. All that had to be done was combining the tracer RNA and crRNA to form simple guide RNA, or sgRNA. If sgRNA and Cas9 combine, they form a two-entity complex rather than three, and this complex has the ability to identify the fourth chromosome in any individual diagnosed with Huntington's disease. Target the HTT gene and read the DNA to find the CAG repeats causing the mutation. Once the CAG repeats are located, they can be cut very precisely by the complex and remove the exact amount of CAG repeats that are excessive, depending on the individual. In the same way, CRISPR was used in bacteria to kill viruses. So this new complex cuts targeted diseases in the same way the effector complex cut the viral DNA in bacteria. Thus, CRISPR can potentially cure HD in this way. In regard to the economic factor of science, on top of the fact that CRISPR-Cas9 can save people as desperate as those with HD, which is, according to Kelly from St. Andrews Healthcare, one of the worst diseases on Earth. Based on Medline Plus, CRISPR-Cas9 is the cheapest gene editing system known as of now. This makes Gage Thomas and other researchers from the National Institute of Health, or NIH, say that there are multiple gene editing systems developed other than CRISPR-Cas9, such as transcription activator-like effector nucleases called TALENs, zinc finger nucleases called ZFNs, and homing endonucleases or meganucleases. Yet based on ArcInvest, CRISPR-Cas9 is 3 to 6 times cheaper than TALENs and other genome editing solutions, with Robert Sanders from Barclay News stating that in some cases CRISPR-Cas9 can spend less than $100 on supplies. According to Patel, Anisha M., and others from a journal made at NIH, to provide healthcare to people with early stages of HD before the use of CRISPR, the costs were from $22,797 to $31,683. For late stages, up to around $95,000, and for middle stages, up to around a whopping $129,000, and the patient will still not be cured. This is a huge difference in price and a vast difference on who can afford to treat themselves from such a harmful disease. People with HD know that they will face a very cruel condition in their older ages, and a cheap, effective, and economic-friendly solutions such as CRISPR-Cas9 compared to the previous solutions can be what HD patients are forever grateful for. However, there is an ethical negative to CRISPR-Cas9 that can reverse the positive effect of CRISPR-Cas9 on HD. Lin and others on the nucleic acid research team in Oxford academics conducted a study to further investigate the errors that CRISPR-Cas9 can cause, being a fairly new developed invention in 1987, according to Ishino from NIH. The researchers found that CRISPR-Cas9 causes mutation in 114 off-target locations, including DNA and sgRNA bulges, and many base mismatches that aren't complementary to one another. This resulted in the conclusion that off-target insertions, and in the case of HD, deletions, have a chance as high as 45.5% of occurring when CRISPR-Cas9 is used on a patient. To prove this point, Naya Kathy wrote about researchers from the Francis Crick Institute who conducted a study on gene editing using CRISPR-Cas9 and found that while they used CRISPR for small insertions and deletions, 16% of samples caused large unintended mutations. Given that HD requires the deletion of 40 or more of the CAG repeats, which is not a small deletion, there is a much higher percentage that an issue is to occur to HD patients. For a patient with HD to pay money and live on the hope that CRISPR-Cas9 will save them, the CRISPR-Cas9 and the sgRNA may locate the wrong base sequence in the HTT gene and, at the worst possible scenario, target the wrong chromosomes. Inaccurate deletions of the CAG repeats can be lethal with a case like HD. This chance of off-targets give a fairly high percentage that someone with HD can suffer more, which is very unethical providing that a patient with HD already suffers greatly. Although there is serious ethical considerations in terms of off-target mutations caused by CRISPR-Cas9, leading to mutations in already harmed individuals affected by HD, according to NIH, 73.5% of individuals with HD die due to the disease. According to Tan Victoria from HD News, fatality is not the worst factor of HD since the brain of the patient does not function properly. They cannot perform any regular day-to-day actions, and they know that they will die eventually, causing the mental disorders leading up to death to increase even more. Due to this, even if CRISPR-Cas9 has a percentage of mutations, the chance of even being able to cure HD patients in this method and low cost for accessibility is a major advancement and could change many individuals with HD's life as well as their family forever. In addition, CRISPR-Cas9 shows great progress in gene editing technology and gives hope to scientists around the world on the benefits, effectiveness, and applications of CRISPR-Cas9 in the future. Thus, the positives of CRISPR-Cas9 in curing HD outweigh the negatives to a great extent.